Hi guys, welcome to the video tutorial for chapter 10.2.2 and 10.2.3. Today we're going to be looking at escape velocities, specifically the Schwarzschild radius, and also in determining the potential inside a charged sphere. So our first learning objective is actually closely related to our previous lesson on escape velocities in chapter 10. This time we're talking about a slightly more specific physical situation, and specifically a black hole. So we know that a black hole is able to pull in or attract through the gravitational field things moving as fast as the speed of light, okay? So even light cannot escape a black hole, hence its name. Now, a certain radius from the black hole, light is no longer able to escape that. And that is essentially the Schwarzschild radius, where nothing can escape the gravitational pull of this object, okay? So what we're going to do is we're going to make some substitutions for the radius r and the escape velocity, okay? So escape velocity we're substituting as the speed of light at the radius r. Okay, and then so essentially the radius for the escape velocities traveling at the speed of light is going to be at a particular distance. Okay, so let's have a look at what this really means with an actual example. Okay, so here we want to calculate the Schwarzschild radius of the Earth. And so let me just put this down here. So 2, just straight substitution, 6.67 times 10 to the minus 11. So we're just going to go into some simple computations. Times 10 to the power of 24. And that was given to us already. 3 times 10 to the power of 8 is the speed of light. And if you punch this in your calculator, you'll get about 8.9 times 10 to the minus 3 meters. And this would roughly translate to 8.9 millimeters. Okay, so if the mass of the Earth could somehow be reduced such that the radius of the Earth was 8.9 millimeters, then anything lower than that, the speed of light wouldn't be able to escape that, okay? All right, so interesting little way to think about that, I suppose. This next part is sort of a bit of an enrichment mixed with Chapter 5 stuff. So this is about geosynchronous or geostationary satellites. So something like our moon is a geosynchronous or geostationary satellite. It orbits at the same speed that the Earth rotates as. And so essentially the time period for the rotation of the moon is at a particular circumference of the Earth. Let me just okay, just had to look up something here. So essentially what we're saying is the distance, so this is really just using displacement over time. Okay, so very simple mechanics formula, displacement over time. So time being the period it takes for one full rotation, okay? And if you smash those two guys together, you get Kepler's third law of planetary motion. Okay, so if you will study more about Kepler's laws when you look at Chapter 5, or if you've done that already and you're watching this video, then you definitely know what is going on here. Okay, so in terms of our learning objective, we want to determine the potential inside a charged sphere. So this is our second learning objective. So for the next part of this video, I want you to pause the video and think about how would the charges be distributed. Would it be as it was in position A or position B? Okay, spoiler alert. So I'm going to be revealing the answer right now. So the correct answer for this would be B, okay? So as you probably know, the light charges would want to repel each other, okay? So they definitely want to be as far away from each other as possible, okay? So, if you were these positive charges, you want to be as far from each other as possible. Okay, so B is definitely the correct answer for that. So what we do know then is that for a conducting sphere, the charges are located on the surface of the sphere. So a quick little recall that the electric field is kq over r squared. Now we're going to use some different notations right now for big R and little r. So big R represents the radius of the sphere itself, and little r represents how far from the center of the sphere you are moving. Okay, so essentially what we see here is that from the center all the way out to the surface, there is, my pen isn't working, there's no electric field. In the middle of this, okay, my Bluetooth is working, my pen has just chosen to stop working. In the middle of this, you see that it is kq over capital R squared. And lastly, once it reaches beyond the surface, it follows that inverse squared relationship that we know about. Okay, there we go, got my pen back. So this last thing is the one that we've been studying all this time. Okay, so the interesting thing for this is the graph. So as you can see in the graph, from 0 to the maximum radius of the sphere, there is no electric field whatsoever, okay? And then as soon as you reach the surface, that's the maximum electric field. And then it follows that inverse squared relationship. Okay, so next up, what might also be interesting is the gravitational pull of the Earth here. So in terms of gravitational field strength, we see that there's actually a linear increase from the center until you reach the surface in terms of the gravitational pull of the planet. So essentially, if you think about this, this is actually kind of interesting. If you were at the center of the Earth, and we know that gravitational fields are affected by masses, right? And so if you have an equivalent amount of mass all around you, it's essentially attracting you equivalently all around you, which means you experience zero gravity in the center of the Earth. So what ends up happening then is that as you move further and further away, you will then experience a little bit of mass below your feet. Okay, so we just kind of section this off. It might be helpful if we section this off to think about that. Okay, so there's a little bit of mass below you and there's more mass above you. Okay, so then you get pulled upwards by the larger mass. Okay, so this little mass still has a bit of gravitational pull, but not as much as the larger mass. Okay, so as you get further and further away, so let's say you're here now. So now all of a sudden there is more mass below you, but there's still a little bit of mass above you, okay? So you do experience a fairly strong gravitational force, okay, but there's still a little bit that's pulling you this way, okay? And then on the surface of the Earth, this is when you experience the most gravitational field because all of that Earth is directly below you. Okay, so that's the reasoning for our gravitational graph here. Okay, now our next question is looking at sort of a combination of different ideas. Okay, so we're given a physical situation where there's an electric field. We have a positively charged object, and I'm going to color that in red, but it does have some mass. Okay, and we know it's traveling at constant velocity. So there's a lot of information here actually. So first off, if we think about this, this would be attracted upwards in this direction, right? The positive charge would repel it, and the negative plate would attract the positive charge towards it. Now, we know it's traveling at constant velocity. So what this has to mean is, if we imagine this being down, excuse me, the force of gravity must be pulling down on the object. And so, because it's traveling constant velocity, these two forces must be identical, right? If it wasn't traveling constant velocity, let's say it was accelerating or decelerating, there must be a force greater than zero acting on it. Okay, so in either of these cases, it has to be more than 0 newtons of force. But because it's traveling at constant speed, the forces must be completely balanced. And so what we're doing here is that we're just rearranging two different formulas where the forces are essentially going to be equal, right? Fg equals to Fe. And then so in order to solve our question, what we've come up with is essentially a formula or an equation that describes the value of the electric field based on the other quantities given. Okay, so this is a fairly challenging question, but these are probably the most challenging ones that you will experience in your exam. Okay, all right. So hopefully this wasn't too difficult. Okay, and then maybe another time we'll go through this with some calculations and the values inside of it. Okay, but you should be able to do something like this through an algebraic way, although it's not always done like that. Okay. All right, guys, take care for now. We'll see you next time. Actually, just think about this. My brain was actually just thinking about the geosynchronous orbit bit. The moon isn't necessarily a geosynchronous orbit. Where was the geosynchronous orbit? The moon isn't necessarily a geosynchronous orbit. The satellites that normally orbit the Earth are in geosynchronous orbits, okay? And essentially that means that as the Earth rotates, the satellite is always in the same place around the Earth, okay? So if the satellite was launched, let's say, directly above New York City, it will always be above New York City because it's spinning at the same speed as the Earth, okay? The moon is an interesting thing that isn't necessarily geosynchronous, but it's actually I got it confused with the spin of the moon is spinning at the same rate as the Earth. And so what happens is that the face of the moon is the same, okay? But we can talk about more of that when we talk about astrophysics. Yeah, a little bit of extra enrichment indeed for you guys, okay? All right, see you next time. Bye-bye.